For number 15, we know that h of x is equal to this. This is our fundamental theorem of calculus, part 2, according to our textbook. So what this means is that h of x is the same as the integral of f of x dx. Now if I derive both sides, you have the derivative of h of x is actually just equal to the function. Remember, the derivative of the integral is just the function. And the second derivative is basically f's first derivative. Now in this case, they're giving you the graph of this function, okay, and it looks like it goes through 6. Some of the things I know is that f of 6 is 0. This is the graph of f. So f of 6 is 0. I know that f prime of x, that's going to be the slope of the tangent line, is kind of like that. It's positive. Basically, it's greater than 0. Now, think about this. If you want to find h of 6, you're basically doing 6 to 0 f of x dx. Essentially, this is saying, what's the area under this curve from 0 to 6? Wouldn't you say it's below, so therefore, it's going to be some negative area? So it looked like this was negative. It looked like h prime of x, which was f of x, it looked like f of 6 was 0, and then the derivative, the slope of the tangent line, was positive. So it looks like in this case, h of 6 was less than h prime of 6, which was less than h double prime of 6. Choice A. This is the position function given by the following. They want to know when is the particle at rest. Remember, the particle is at rest when the velocity is equal to 0. And then the derivative of this is the velocity. So what I'm going to do is I'm going to expand this before I take the derivative. So if I derive this, I get 2t minus a minus b, and this is a constant. Derivative of a constant is 0. So I'm going to set this equal to 0. I'm going to solve for t essentially. I'm going to add a, add b. You get a plus b equals 2t. Divide both sides by 2. So at time, a plus b over 2. The particle is at rest. This is choice